Now let's work on yet another example. Let's take the rational function f of x equals 1 over x squared plus 12. And let's do the exactly same procedure, determine the intervals where it's concave upward or concave downward, and then find any points of inflection. So we'll start by finding the first and second derivative of this expression. For the first derivative, we do derivative 1 over x squared plus 12. And it's easy if we consider it as the derivative of x squared plus 12 to the negative first power. So by chain rule, this is negative 1 times this to the negative second power times the derivative of the inside function, which works out to be negative 1 over x squared plus 12 squared times 2x. So all of that is negative 2x over x squared plus 12 squared. That's the first derivative. After that, we set to find the second derivative, so it's the derivative of negative 2x over x squared plus 12 squared. And now we factor out negative and then do the quotient rule. We end up with derivative of numerator times denominator minus the numerator times derivative of denominator divided by denominator squared. Since we already had x squared plus 12 squared there, we're going to end up with x squared plus 12 to the fourth power. Then we see that derivative of 2x is positive 2, and then derivative of x squared plus 12 squared by the chain rule will be 2 times x squared plus 12 times the derivative of inside expression, which boils down to negative 2 times x squared plus 12 squared minus 4x times x squared plus 12 times 2x. All of that over x squared plus 12 to the fourth power. Then we notice that we can factor out 2 and x squared plus 12 out of each of the terms. So let's see. There is 2 here, and there is x squared plus 12 term there. Likewise, there is 2 here, and x squared plus 12 term here. So we factor that out. What will be left? There will be x squared plus 12 left out of the first term. Then there is 4x and x left out of the second term. So we're good there. Now, once we have that, we go ahead and cancel x squared plus 12, and one of those x squared plus 12 there. So there is only third power left. And we end up with this expression, which after combining like terms gives us negative of 2 times 12 minus 3x squared in numerator, and x squared plus 12 to the third power in denominator. Then we take out 3 out of the numerator expression. There is 3 here, and this 12 is 3 times 4. So factor out 3, we end up with 4 minus x squared. And then we're gonna bring this negative in, so we're gonna distribute it here and there, so that we end up with 6 times x squared minus 4. All of that over x squared plus 12 to the third power. That's the first and second derivative. So we're gonna need just the results, so I'm going to copy those. Okay, I'm gonna need only final results, so I'm going to copy those. First derivative is negative 2x over x squared plus 12 squared. Second derivative is 6 times x squared minus 4 divided by x squared plus 12 cubed. After that, we set on finding the zeros of second derivative and the points where second derivative does not exist. Setting up the fraction equals 0, this is equivalent to numerator being 0, which gives us x squared minus 4 is 0, or x squared is equal to 4. And then doing the square root with a plus or minus, we get x being positive or negative 2. For the places where second derivative does not exist, we set denominator being 0, and that gives us x squared plus 12 cubed equals 0, so x squared plus 12 is 0, or x squared is equal to negative 12. These have no solutions, because x squared is never equal to a negative number. So there are no places where second derivative is not defined. So the intervals we're gonna look at are negative infinity to negative 2, negative 2 to positive 2, and the third interval 2 up to positive infinity. We put that into a table with the intervals, test points, and the values of the second derivative. For the test points we choose negative 3, 0, and 3, and then evaluate second derivative at each of those points. At negative 3 we're going to end up with this expression, which gives us 6 times 5, and downstairs we have 21 to the third power, so all of this is some positive number. Then at 0 we're going to end up with negative 24 divided by 12 cubed, it's a negative number. And at positive 3 we end up with 6 times 5 over 21 cubed. We put this into the formula for the second derivative. So we see that second derivative is positive on the leftmost interval, negative in the middle, and positive on the rightmost interval. That allows us to claim that where second derivative is positive, we have the function concave upward. Where the second derivative is positive, we have concave upward function. Where the second derivative is negative, the function is concave downward. Well, this allows us to conclude that x equals negative 2 and x equals 2 are both points of inflection. So we're now ready to write the answer. First of all, the function is concave upward on the intervals negative infinity, negative 2, together with the interval 2 to positive infinity. Then the function is concave downward on the interval from negative 2 to 2. And both x equals negative 2 and x equals positive 2 are points of inflection. Okay. In this example, once we have completed all the hard work of figuring out the intervals of concavity up and concavity down, so we figured out that the negative 2 and positive 2 are the points of inflection. Let's have a quick look on the graph of this function. Here is the graph on a rather large scale. So we found that somewhere here at around x equals negative 2 and around here at x equals positive 2 we have inflection points. So in the middle we can easily see that it is a concave down graph. Then to the right it's a piece of an upright U-shape, so it's concave up. And on the left hand it's a piece of an upright U-shape, so it's concave up. That's how we can figure out what's going on from the graph. Now let's work on this example with the trig function. So let's consider f of x being x plus 2 cosine x for x between 0 and 2 pi. We'll determine the intervals where the function is concave up or down and find any points of inflection. So we'll start by finding the first derivative, which will work out to be 1 minus 2 sine x. Then for the second derivative we figure out that it's negative 2 times cosine x. Since negative 2 cosine x is defined everywhere, we need to find only zeros of second derivative on the interval from 0 to 2 pi. Set negative 2x, negative 2 cosine x equal to 0. This is equivalent to cosine x being equal to 0. And the deal here is that this equation has solution being x equals pi over 2 plus pi n, where n is some integer. And the only two solutions that are between 0 and 2 pi are x equals pi over 2 and x equals 3 pi over 2. That will give us the intervals. So let me get this out of the way. So we consider the intervals between 0 and pi over 2 to 3 pi over 2, and 3 pi over 2 to 2 pi. Okay, So let me remove everything that is not needed and put the information that we need back. So we're gonna come up with a table. We have those three intervals and the points of interest, pi over 2 and 3 pi over 2. I'm gonna choose some test points. Between 0 and pi over 2 there is pi over 4. Between pi over 2 and 3 pi over 2 there is positive pi. Between 3 pi over 2 and 2 pi there is 7 pi over 4. And essentially we're gonna put those points into the second derivative. So second derivative at pi over 4 is negative 2 times cosine of pi over 4. Cosine of pi over 4 is square root of 2 over 2. We get negative 2 times that number, negative square root of 2. At pi we get negative 2 times cosine pi, so it's negative 2 times negative 1, which is positive 2. And at 7 pi over 4 we get negative 2 times square root of 2 over 2, which is negative square root of 2. In the end, those are the results that we've got. So we notice that the negative square root of 2 is less than 0, positive 2 is greater than 0, and negative square root of 2 is also less than 0. Since the second derivative is negative on the leftmost and the rightmost piece, we claim that the function is concave downward there. And for the middle piece, the function is concave upward. Hence, those 2 points of interest are exactly points of inflection, because concavity changes from downward to upward and from upward to downward. So x equals pi over 2 and x equals 3 pi over 2 are points of inflection. And we're ready to put the answer. And it reads that f of x is concave upward on pi over 2 to 3 pi over 2. F of x is concave downward on 0 to pi over 2, together with 3 pi over 2 to 2 pi. And x equals pi over 2 and x equals 3 pi over 2 are points of inflection. In this example, once we're done figuring out what's going on with the graph of the function, so it's concave downward, then concave upward, then concave downward, and pi over 2 and 3 pi over 2 seem to be the points of inflection. Let's have a look on the graph of this function x plus 2 cosine x for x between 0 and 2 pi. And remember, pi over 2 and 3 pi over 2 were the points of inflection, and we clearly see on the graph the starting piece looks like a part of upside down U shape, so it's concave down. The middle piece looks like a part of an upright U shape, so it's concave up. And the right piece looks like a part of upside down U shape, so it's concave down. And those 2 blue points look like the points of inflection. We actually found all of that numerically, and the graph checks out.